yeah, let's move on to the last team, which is also the the largest team. I do understand we were a little bit overstaffed on this one for the semester. So yeah, apologies from my end for this. But I think, it looked pretty good to me in terms of how you figured out the task allocation and how the collaboration works. So I'm really excited to learn about the outcomes for this one. We had many different moving parts, so yeah, we'll see how it goes. But without further ado, please take it away.
Yes, so we're the energy and building team, and today we have Joseph, Gia, me, Anupha, Jessica, Han, Kavya, Johnny, Shivam, and Joe with us. Um, so let's get into it. The first thing we're going to talk about is our models. So last semester we looked at a lot of different machine learning models, and this was their performance on both training and testing dataset on the Georgia dataset. And we can see that the gradient boost did the best for the heating dataset for testing, and MLR, our traditional machine learning model, did the best for cooling. And this is the SHAP analyses for both MLR and gradient boost for the cooling and heating model respectively. And the reason we do that is so that we can see which are the features that have the most impact on the model. And we can see that features like roof area, type, and height, they have the most impact, whereas orientation, energy code, the year it was built, have the least impact on the energy prediction. And this is consistent with both heating and cooling. And this is the SHAP analysis for our artificial neural network ANN model. And the reason we did that, even though ANN didn't perform as well as gradient boost and MLR, is to see if the feature analysis did carry over. And we can see that that is indeed the case. High roof area stories, they are still more important as compared to orientation, the year the building was built, and energy code. And now we're going to talk about the map.
Yeah, so to introduce the map a little bit, the map was kind of intended to be a visualization of the model that we worked on last semester. So on the left, we have the work we did last semester. So that includes the game, which is able to predict the energy load for a single building. And then we also have the model. And so this semester on the right, we created a visualization. And this basically takes like maybe 2 seconds to run, and it runs on maybe 3,000 plus buildings at once. And so it just outputs this visualization on the right. And we can kind of see that the darker buildings are the buildings that take a little bit more energy. And then buildings that are a little bit lighter are buildings that don't take as much energy. And this is for cooling right now. And to kind of separate the map into components, we mainly use our building dataset from Overture Map. So this kind of gives us the GeoJSON for the map. And that's the only thing we need for this map. We just need to download a GeoJSON, and then we can just put it in the backend, and then it creates this visualization. And some of the main libraries that we use are MapLibra, MapTiler, Turf. So these all just kind of help create the visualization. MapLibra specifically is for the 3D buildings, and then MapTiler is just the background, and then Turf is for the backend calculations that we see on the right here. So these are all the model parameters that the model takes in. And since Overture didn't really have these parameters, we had to calculate them. Either that, or we had to find another data set that had these parameters, but it was kind of hard because in theory, we would want this to be very general, and it's kind of hard to find data sets for all the entire world, basically. So the model parameters here, we have building type. So now it's randomly assigned since we changed the map back from Ithaca to Atlanta. So we just kind of randomly assign the building type, and then building shape. Shivam can talk a little bit more about that. I think he uses the building polygons, the nested polygons, to calculate the shape. And then orientation is just, we take the longest side of the building, and then we find the angle between that and the positive x-axis. Height, it's given in Overture, and if not, then we calculate it based on an average given in the Comstock documentation. And same with stories, it's given in the Overture, and if not, we calculate it. wall area, window area, these we calculate. Roof area, we use the shoelace formula. And energy code and HVAC, these are kind of different. These are based on the building type. So maybe a building type is like a large hotel or a small hotel, or maybe like a restaurant. So all of these will have kind of different energy codes and HVAC systems. So we kind of base it off the building type.
Yeah, and I guess to give a bit more insight on building shape, essentially, as Jessica mentioned, we kind of take the polygon data, and then right now, as so far, we have a bunch of if statements, and it kind of runs through them to kind of see, like, I think the 11 different types of buildings that we have. So for example, if we have a courtyard, it would essentially check the polygons of the outside building and find out, like, is there a separate polygon that's within that polygon? So if you know that information, that kind of implies that there's a shape within a shape, and for that to happen, that means that the inner shape is kind of opened up, and that kind of implies that, oh, there's a courtyard in between inside the building and stuff like that. And then going down, we have like separate ones for each different building type. Then once kind of like these different parameters are kind of joined into our GeoJSON file, we kind of use that as the user input, and through that we're actually able to get building prediction data for the entire GeoJSON file, or the buildings that we're actually trying to look at. Ideally, in the long run, this would be for an entire city or entire regions. But after that kind of works on load, and it's actually pretty fast, we're able to load in all the predictive data. And you can kind of see that for the current front end web app that we have, you can kind of toggle in between the predictions for the cooling loads and the heating loads. And then kind of along with that, we kind of noticed that we added a color gradient. So just from a quick look, you can kind of see that the darker buildings are the ones that kind of have higher heating or cooling prediction loads, versus the lighter ones are the ones that we kind of predicted to have, comparatively, the lesser loads. And we also added a features panel. So when you click on a certain building, you're kind of able to get specific data on it, specifically like the heights, what kind of orientation it has, the different building shapes that it's, that we've kind of predicted it to be, and then also the respective cooling and heating predictive loads. So I think this is a very good step that we've made, because now, if we have the data that we need, in like less than a second or so, we're able to kind of get like all this data or visualization for an entire swath of the city. If we go to the next slide, we can kind of see that some of the pros that we have is that it is pretty fast. So we can kind of give a quick idea of where some buildings, like we see here, the very dark ones are the ones that relatively are like, they have a lot of heating and cooling consumption. And because of the usage of MapLibre, it is very lightweight, and we are calculating everything. So we're able to basically instantly get everything for the entire map that we're looking at. Now, again, as we mentioned before, there are some things that we do want to work on. Currently, we do have to manually import the GeoJSON that we want to look at. So before, it was kind of like the Ithaca data set that we had to import, and then same thing with the GeoJSON for Atlanta. It isn't something that's streamlined in. And then it is also that we don't have a model that kind of takes into account that you're looking at this region. And so given this region, this is what the estimated predictive outputs would be. It's more or less, we kind of have to train it depending on the data set of the region we have. So whether that be the Ithaca data set, we have a model for that, or the Atlanta data set, we have a model for that. Or let's say we were trying to pick a different city, we would have to create a model based on that data set. So, but if we go to the next slide, this kind of peeks into things we could do for, our next steps. So as we mentioned before, ideally, we would want an automated GeoJSON support, so we wouldn't have to worry about importing for the specific regions that we're looking at. And then ideally train for different regions, so we wouldn't have to worry about confining ourselves to certain areas and being able to expand. And as mentioned before, things like building type and even like building shape and stuff, since we don't have there's like many different features that we kind of had to add predictions of our own because it wasn't supplied to us. So ideally, we would want to move in and kind of instead of having random or have different occurrences of buildings, or kind of work on the estimations for building shape to see how we can have a better predictive idea of like, is this really a square, or is this really an L-shaped, or what categories do these fall into? And some other ideas that we had was like foliage integration. So we do have an idea that trees, especially in places that there's a lot of trees and buildings that are not so tall, you kind of get a lot of shade from that, and that does have an effect on energy consumption. But currently, the model that we have and the map that we have doesn't really take that into account. But we do know of data sets, and we do know of other web apps that have integrations for shading. And the idea is that hopefully we could also integrate that into it. And ideally, the biggest one is to be able to deploy this for widespread public use.
So the next part of our energy group was to make a plugin for Rhino with the ML model we had. So when we started the semester, we had a version of the model that was working, and there were two ways to go forward with it. One was to predict the energy consumption of existing buildings where the map came in, and then was the other way forward was also to predict the energy consumption of buildings that are yet to be designed. So for future buildings that architects might build. So that was where the Rhino plugin idea came in. So we want to build a Rhino plugin that lets architects sketch, import, or edit simple building masses, and the features of those building masses be read by the plugin, and the ML model then be used by the plugin to predict the energy load for the design that the architects for Atlantis climate in our case. So how the model works overall, how the GH component works overall is, can you go to the previous slide, Anuba? So how the plugin works overall is that the plugin is given a ONNX model input, and which initiates an inference session, and the input metadata from the model exposes each of the parameters, names, data types, and shapes. And then the component pulls each GH input value and matches it with the ONNX model's input shapes. After that, it executes the ML model, and the output is a list which contains the energy load. And the first element from that 1D array is pushed back to the GH output. Can you go to the next slide? So, GI, do you want to talk about this slide?
Yes. So then we use the grasshopper to extract the building parameter, like the building height, the number of story, wall area, roof area, and window area. And then we can plug into our grasshopper plugin. Yes.
Yes. So, so as Jay was mentioning, we want to make the whole process intuitive. So if somebody's modeling it in Rhino, we extract the parameters and then feed it into the grasshopper plugin. So the way forward with the next steps with this plugin is, as I was mentioning earlier, this plugin is the intent for this plugin when we started was for predicting the energy consumption of future buildings that architects may be designing. But there's also opportunity where with the map that Jessica and Shivam were working on, that we can query a portion of the map and then load geometry from that map into the Rhino environment so that retrofit decisions may also be made using the plugin. Apart from that, currently our model is trained for Atlanta and for the building typology distribution of Atlanta. So Atlanta might have a higher concentration of educational institutions or commercial institutions than other building types, I'm guessing. But somebody else in another part of the world may want to predict the energy for a different climate type and for different distribution of buildings in their region. So we experimented with both ONNX and joblib file types for the plugin, and we still haven't concluded which is the better model to go forward with. The benefit we have with ONNX is that it does not have any Python runtime dependency. ONNX works very well with C#, just using the Microsoft ONNX runtime module. But at the same time, joblib is doing a better job at reading the actual names of the parameters rather than just giving the number of parameters that are there. But the problem with joblib is that it involves calling CPython through PythonNet, and then we had a lot of issues with DLL file paths and mismatched versions of scikit and numpy and all that. So those would be figuring that out, and the integration with the map would be the main way forward, the next steps with the plugin.
All right, next we can talk about factoring in flora to using in our model as well. So we wanted to see like what are the effects of plants on the surroundings, because if you have like a tree, then it would obviously provide shade to the building, which would in turn reduce the amount of energy it's consuming to cool down the building as well. So two of the main methods that we considered was first normalized difference vegetation index, which was the NDVI analysis, as well as the tree count seg height model as well.
Unfortunately, we did run into a few issues when attempting to implement these models. First of all, we discovered that NDVI actually did not serve our intended purpose because it just locates the locations of the vegetation as opposed to calculating the heights, which would help contribute to our model. And while tree count seg height does contribute the desired data of calculating the height based on the satellite imagery, we found that it was a very resource intensive process that actually wasn't even able to be run on our personal devices. And so that slowed down the workflow a little bit too much. And so moving forward, our next step would mainly to be finding a more lightweight or efficient way to extract the height of these plants from satellite.